Okay, so 5 out of 100 resulted in 0.58 or less. So, if, and again, this is a big if the freshman population proportion was to be 71%, we would have had a 5% chance only of getting a sample that's that much lower. Does that make sense? So there's only a 5% chance that a population proportion of 0.71 would result in a sample proportion of 0.58. And so, could it have happened? Sure. Based on our one sample, could the freshmen actually also have a 71% ownership rate? They could. But there's only a 5% chance of that actually being the case. So more likely than not, the population proportion for the freshmen is lower than 71%. Do we follow that? In fact, there's a 95% chance, if there's a 5% chance that it could have happened, there's a 95% chance that the population proportion for freshmen is actually not 0.71. It's probably lower. Okay? Does that make sense? Okay. On part B, based on your answer to A, how likely is it that a sample of 52 from a population with a cell phone ownership of 7 would 5% likely? We already said that, which is not very good. C says, is it possible that a sample of 52 from a population with a cell phone ownership rate of 71% could have had a sample proportion of 0.58 or less? Is it possible? Yes. 5% means it's possible. So yes, it is possible, but only with a 5% chance. Well, they're kind of just asking questions I've already talked about. In part D, what conclusion can you make about freshman cell phone ownership compared to ownership by juniors? There is a 95% chance that the freshman population ownership rate is actually less than 0.71. Is actually less than the 0.71 junior rate. So taking one sample of freshmen is a little, it's not conclusive. You know, we can't say no way is it the same as the junior 0.71 rate. But if you look at the simulation, it gives us an idea as to how likely that would be. Does this make sense? Okay. Any questions so far? Okay. We're going to switch the scenario here for a minute. This says, let's say we have a population with a 0.25 proportion. So I'm going to go back to my simulation page. I'm just going to look at this recording. Anything? I think it's going to show that screen. Oh, I hope so. Yeah. Okay, good, well, we hope so. I kind of thought it was just recording something else, but who knows. All right. Anyway, population proportion of 0.25. Let's say we have a population with a 0.25 proportion of being 65 years or older. 65 years or older is that number. I don't want that to be misleading. So let's just say retired. I would just cross out that 65 years or older and replace it with the word retired, because then you don't have that extra number floating around that might be confusing to you. So of being retired. So in our population, we know that the proportion, the chance of being retired is 0.25, 25% chance. Let's take different size samples from this population and see how the sample proportions behave. Okay, so we're going to talk about how the size of the sample we choose affects our sample proportion. Use the program to simulate a population proportion of 0.25 for various sample sizes. We're going to do 100 simulations. So the first sample size is 10. And we're going to do 100 simulations for everything. And then I'm going to run that simulation, hit OK, and there are my 100 numbers. If I only sample 10 people, now look at the range of my results. The lowest is 0. So on some of my simulations, some of my samples of 10 people, I get no people that are retired. And I also, in other cases, get as high as 60%, like 6 out of my 10 people are retired. So that's kind of luck of the draw. Now, by the way, when I hit that simulation button, and somebody else goes on their homework tonight and hits that simulation button, our numbers and our simulated numbers might be different from each other. It's not going to produce the same ones every time, because it's literally like throwing this all into a bag and picking out randomly. So our numbers might be slightly different than the solutions on the homework. But if we look at this sample size, it's ranging from as low as 0 out of 10 to 6 out of the 10. So the low to high sample proportion values are from 0 to 0.6.
I got 0.7.
Okay, right. So Jacob ran it on his phone, and he got something slightly different. So that's because ours ran, just randomly came up with different simulations. It's not doing the same one every time. Now I'm going to increase my sample size to 20 and see what happens. By the way, that range is pretty large, right? 0% to 60%. That's not helping me see exactly how many are retired. I'm going to up my sample size to 20 and rerun. And my lowest is still 0. My highest is now 0.55. So if I put that in, 0 to 0.55, it's getting a little bit closer knit, but not by a ton. If I jump up to 50, and run that, my lowest is 0.06 to 0.38. 0.06 to 0.38. It's getting closer and closer knit, 0.06 to 0.38, which is 0.38. What is that range? 0.38 minus 0.06. And lastly, with 100 simulations, change that to 100, run the simulation. My lowest is 0.13, and my highest is 0.34, so 13% to 34%. So 0.13 to 0.34, which is a range of 0.21. Do you see how these keep pinching in closer and closer to surrounding our 0.25? Right? 0.25 is somewhere between all of these. but we keep pinching in closer and closer to 0.25. Do we see that? Yes?
Like, how do I calculate the range?
You just do highest minus lowest. So the moral of this story is, the bigger your sample size, the more accurate it will be to the actual population. So the bigger the sample size, the closer the sample proportion, and I'm going to use a symbol for that, the closer that will be to the population proportion. Okay? And then the next part says to run it one more time, but I'm going to use the sample size of 50, but I'm going to increase my number of simulations, okay, to 200. Now, do I want to do this? I'm going to do it for 100 first. I'm going to go back to that sample size of 50 for 100 simulations. I'm going to do that, go back to that. Now, this is going to talk about a confidence interval. So, find the value that represents the 5th percentile. Now, I went back to 100 because what's 5% of 100? What's 5% of 100? Just 5. So the 5th score on my list, maybe not. We want the score on my list that's higher than 5%. Because to be in the 5th percentile, you're higher than 5% of the people. So here are the lowest 5%. 1, 2, 3, 4, 5. So this number is your 5th percentile cutoff. So 0.16. Yes?
Wait, didn't you say I have to do it for 200 simulations?
I know, I'm doing it for 100 because 5% of 100 is easier. So the 6th score, which was what, 0.16? That is the 5th percentile number. That's the sample proportion number that's the 5th percentile. For the 95th percentile, one second, Anthony. For the 95th percentile, I need the number at the top that's higher than 95 of the rest. So if there's 100 total simulations I just did, that's the 100th, 99th, 98th, 97th, and this is the 96th number, which is higher than 95 other ones. So 0.36 is our 95th percentile. And so this talks about a confidence interval. So we are 90% confident. So we are 90% confident that our P, the population proportion, is between 0.16 and 0.36. If we were only taking samples to gather our information, you find the 5th percentile and the 95th percentile, and then that gives you your 90% interval from 16 to 36%. We know that the population proportion of people who are retired is between those two numbers. And we know that with 90% confidence, right? Because 5% to 95% is the 90% interval. Okay? We'll do more with confidence intervals, but if I had run the 200 simulations, what score would I have to go to for the bottom 5%? 10 scores, right? Because the 5 percentile out of 200 scores would have been the 10th score into your list. Does that make sense? Okay, so I went back to 100 just because it was easier, but if you did 500 simulations, you would have to do 5% of 500, and you'd have to take that number score off the bottom, and that number score off the top, and then you're 90% confident it happens between those numbers. Because they told me the population proportion was 0.25. At the very top, they said the population proportion is 0.25, and so I was just kind of showing how those numbers started, like 0 to 0.4 was really wide surrounding 0.5, but then as your sample grows, we surround 0.25 more closely. Okay?